Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical. And we are talking about the welding of metals. In this particular presentation, I will be focusing on the different ways, methods, principles used for improving the weld joint properties. Okay, accordingly, the content for this presentation has been designed. So, here improving the load carrying capacity of the joint which is being developed. This is the first thing where, like say in autogeneous welding, you see what we do, we just try to ensure the proper belting of the fixed surfaces followed by the rapid cooling. But if the metal is like transformation hardening kind, then under the welding conditions due to the typical weld thermal cycle imposed, this region is automatically hardened due to the transformation hardening. But if this is not the case is little different where the transformation hardening is not involved. In that case, what we have to do to ensure that our the weld joint is strong, weld metal. So, weld joint, there are two main aspects that will be determining the joint strength of. So, the one is the kind of the weld metal and another is the heat affected zone. So, we need to have the good properties of both weld metal and the heat affected zone. So, in case when the metal is not transformation hardening kind, then we have to add the suitable kind of the filler metal in order to achieve the matching characteristics or the better characteristics of the weld metal. So, there we try to use the suitable kind of the filler that can offer us the desired set of properties. As far as the HHT is concerned, certainly the structure of the heat affected zone is to be controlled and regulated in such a way that it offers the reasonably good properties to offer the desired joint efficiency and the joint performance. So, there are two main zones as far as the performance of the weld joint is concerned. One is the weld metal and another is the heat affected zone. If the failure is occurring from the base metal, then it does not bother us as far as the welding is concerned. Why? Because the base metal characteristics are, they will be based on the kind of the design requirements. Okay. So, the one aspect is, let us improve the load carrying capacity of the weld metal itself by choosing the suitable kind of filler. Another is the reducing the stress resistors. We know that the welding most of the time introduces the variety of the stress resistors in form of the weld defects or uneven surfaces or improper the weld bead profile. So, all these aspects or the weld toe we have with the high bead angle. So, the weld toe also will be causing the significant stress concentration. So, what we have to do, we have to make all the efforts so that in whatever form stress resistors are present, they are minimized or eliminated in order to improve the performance of the joint. Okay. So, we will be talking about the various techniques which are used for improving the performance of the weld joint through the elimination or reducing the stress resistors. Say one is the trig dressing, another is the short peening, and third is the machining the fillet in case of the weld toe or the fillet weld joints. Then invariably due to the typical weld thermal cycle introduced during the fusion welding or solid state joining. So, the nature of the thermal cycle is such that it is different at the different locations. So, because of the localized weld thermal cycle coupled with the heating, soaking followed by cooling, which is different in the different zones in the vicinity of the weld joint and also in the weld zone. So, what will be happening? This will be causing the differential, because of this differential expansion and contraction. So, because of the unique thermal cycle imposed, weld thermal cycle imposed during the welding at each location in vicinity of the weld joint. So, this leads to the differential expansion and contraction during the heating and cooling, and this in turn results in the development of the residual stresses. This is also known as thermal stresses. Okay. The thermal stresses contribute significantly towards the residual stress development, and most of the time in fusion welding the residual stresses are tensile in nature. So, whenever we have the tensile residual stresses in the weld joint, it reduces the load carrying capacity of the weld joint against the tensile loading, and the also the fatigue resistance under the tensile condition is minimized, and therefore it becomes important to reduce the residual stresses or eliminate the residual stresses from the weld joint, so that the performance of the weld joint can be enhanced. So, various methods are used for this purpose. One is like overloading. Okay, overloading, like here we load beyond the yield point, so that the locked in strain is relieved, or ultrasonic treatment is given, so that here the resonant frequency is identified and then vibrations are given accordingly in order to relieve the locked in strain, or the stress relieving heat treatment is done. Here we just heat the weld to the higher temperature, so that the yield strength is minimized, and a reduction in yield strength will be reducing the or eliminating the locked in strain, which contributes towards the development of the residual stress. That is the idea behind the stress relieving. So, these are three methods which are related with the development of the residual reducing the residual stresses in the weld joint. Okay. Then to improve the weld joint properties, it is very important that not just the stress ratios are eliminated or residual stresses are reduced, but it is also important that the each zone, whether it is the heat affected zone or it is the weld metal, these have the desired set of the properties, and how we can ensure the desired set of the properties through the proper control of the microstructure, because during the fusion welding we get the cast weld structure usually, and the heat affected zone as per the typical weld thermal cycle which is imposed, and therefore we get lot of heterogeneity in terms of the microstructural variation across the weld joint, like the base metal, then heat affected zone, and then the weld metal, and likewise heat affected zone other side and the base metals. We get lot of heterogeneity, and according due to this variation in the microstructure, properties also change accordingly. So, in order to have the good performance in terms of the mechanical loading, load carrying capacity, in terms of the corrosion resistance, it is important that the properties of the microstructure and properties of the weld joint is stabilized. Okay. So, what we do, we try to do the post weld treatment. Those post weld heat treatment is one of the aspects. So, post weld heat treatment helps in, like say, especially in steel welding, hardenable steel welding, the heating helps to eliminate or diffuse out the hydrogen if it is involved. Hydrogen is dissolved in the weld metal, which can otherwise promote the embrittlement as well as the cold cracking tendency. If the steel is hardenable, then it will also be leading to the embrittlement of the weld and the heat affected zone, weld metal and heat affected zone. So, embrittlement means increased hardness, reduced toughness. So by tempering we can increase toughness with the marginal drop in the hardness. So, this is realized. So, these variation in properties also as per the requirement can be realized through the control of the desired microstructure, so as to obtain the desired set of the properties. So, these are the three broad categories. One is choose the suitable filler, so that the weld metal of the suitable composition and properties is obtained. Another is eliminate or reduce the stress ratios, reduce the residual stresses, and develop the suitable microstructure, so that the desired set of the properties are realized. Okay. So, this is the first aspect. Like the weld joint in general in the butt joint configuration offers the maximum joint load carrying capacity, maximum joint performance, because inherently there is no stress razor for this kind of arrangement as compared to that of the fillet weld. Fillet welds under the identical conditions offer the lesser strength due to the inherent stresses or stress concentration present at the toe of the weld. Okay. So, here like say in the T weld joint, this is the fillet weld. So, here the stress concentration at the toe of the weld is high, and therefore, what we find, especially with regard to the fatigue resistance, if we see increasing the strength of the weld metal, in case of the butt joint it helps in increasing the joint fatigue resistance significantly, but in case of the fillet weld, because of the higher stress concentration, increase in the fatigue resistance is not much. So, here it is important that the suitable type of the weld joint is selected. Okay, efforts are made to have the butt joint, and if we can avoid the presence of the fillet weld joint. Okay, then developing the sound weld joint. As I have said, like if there is the weld metal produced through the fusion welding, and if it is having either say crack at the center or porosity or inclusions in the weld metal, then these defects in form of the porosity, inclusions or cracks, these are going to act in two ways. First, they will be reducing the load resisting cross sectional area. Okay. So, this is one, when defects are present, like say under this tensile loading. So, they will be actually reducing the load resisting cross sectional area, and therefore, nominal stresses will also enhance. And the second one, whenever there are defects, the stress concentration will be high. So, that stress concentration is found proportional to the square root of the size of the defect and the defect radius of the defect. So, if it is like say the crack like this, so the radius of the crack tip and its size A. So, like this. So, the A greater the defect size, greater will be the stress concentration, and finer is the crack tip radius or the radius associated with the defect, then that will be increasing the stress concentration. So, a square root of the A by that governs significantly the stress concentration around the defect. Therefore, it is important that the defects are eliminated. When the defects are eliminated using suitable approaches, then that will help that will avoid the situation of reduction in load resisting cross sectional area, or that will also avoid the stress concentration, okay, due to the presence of the defect. Okay, controlling the weld thermal cycle is the another way, like if the weld is made using the high heat input, H net is very high. Okay, then the weld zone as well as the heat affected zone will be cooling very slowly. So, HAZ and the weld metal, if these are being cooled slowly, then the slow cooling rate will slow cooling rate will be leading to the coarse grain structure and increased segregation tendency of the impurities at the center of the weld. That will increase the solidification cracking tendency, and coarse grain structure will reduce the strength of the joint. So, we need to see that the proper weld thermal cycle is imposed. Okay. There is another possibility also, like in case of the hardenable steels, if the weld joint is made and if the carbon equivalent associated with the steel is very high, say 0.6, then without any kind of the preheat, if the weld joint is made using the welding process like arc welding, then there is every tendency that a significant embrittlement of the weld metal and the heat affected zone will be taking place. So, in order to avoid such kind of the degradation in properties in terms of the loss of toughness, loss of ductility and increased hardness, it is important that if the proper weld thermal cycle is imposed through the preheating of the weld, then such kind of the hard embrittlement of the weld joint and formation of the such kind of the microstructure can be reduced through the suitable preheat. So, the weld thermal cycle can be used to adjust the microstructure and mechanical properties to some level for improving the joint performance. Even if this is not doable, then we can go for the post-weld heat treatment, so that the desired set of the properties are realized. This is the another aspect about which I have talked, like say in case of the autogeneous welding, not much can be done, because as per the weld thermal cycle imposed, the microstructure and mechanical properties of the weld zone will be governed. But if this is not the case, if we have prepared the groups, and then if we want to realize the desired set of the properties in a weld joint, then what we do, we choose the filler of the suitable composition, so that the even after the dilution, the weld metal of the desired composition is realized with the desired microstructure and mechanical properties. So, here idea is choose the filler or electrodes suitably so that the weld metal of the desired composition and desired properties is realized to attain the desired set of the mechanical properties. So, here what we have to keep in mind, not just the composition of the filler or electrode, but also the kind of the dilution which is taking place. Dilution is about the intermixing of the molten metal which is coming from the electrode and the base metal, and that will depend upon the multiple parameters like the net heat input that is there in the kind of the type of the joint which is being made, whether it is groove weld or the fillet weld, etc. Then, so these are the overview related aspects of the weld metal which affect the structure and properties of the weld joint. Okay, so if those are used, then the performance or load carrying capacity of the weld metal can be controlled in better way. Now, as I have said, the weld joint invariably produces a lot of stress residues. Okay, so these stress residues, like these, can be present at the surface in form of cracks or in form or near surface, like in form of inclusions or the porosity. Okay, stress residues may also be there in form of the weld toe. Okay, like say this in fillet weld, at the toe of the weld there is a high stress concentration. Even in the butt joint, if the weld bead angle is not proper, then at the toe of the weld also stress concentration becomes very high. So, poor weld bead geometry means it is either the weld surface is very rough, or the reinforcement is too high, or it is low, like underfilling case is there. Then all those will be leading to the situation, or will be acting as, all these aspects will be contributing as a stress razor for localized enhanced presence of the stress in these areas, like say that weld toe of the weld, or the rough surfaces, or the underfilled zones or undercut wherever the defects are present. Okay. So, in all these cases, since the stress concentration will be high, and how it is given, like say this is the weld joint. Okay, okay, and here the load is applied. So, for a given load, and the given load resisting cross sectional area A, we get the nominal stress P by A. Okay, but when we try to see the maximum stress in presence of some defect, okay, in presence of the defect, say the defect of length L and the radius is R, tip radius is R of the defect, then the maximum stress around the defect, that will be of the twice of sigma naught A by R square root. Okay. So, here the twice of A by R square root is the stress concentration factor. Okay, stress concentration factor. So, here the maximum stress will depend upon the size of the defect and the tip radius. Therefore, it is very important that these defects are either modified or these are eliminated. Okay. And how we can do this? We can do through the controlled surface layer deformation. We can do hammering and peening in the areas where there is irregularities, or wherever the stress concern, wherever the fillet radius is very fine at the weld toe also. We can also do the remelting of the weld toe area or the surface layers of the weld bead to eliminate if there is any defect. So, what we do in this case, say this is the weld joint, and if in the weld toe, if we have the defects here, or if the weld toe is very having the radius very sharp, bead angle is very high, then what we do, this is the weld zone. So, what we do, we apply heat in localized way with the help of suitable heat source. Usually this is the TIG arc, okay, because TIG supplies the heat only for the remelting, and it does not supply any kind of the filler. So, the TIG arc is fed. So, here localized melting at the toe of the weld will be realized. So, when the remelting takes place, if there are impurities, defects, inclusions, porosity, that those will be eliminated, and the bead angle which was initially sharp, that will get also reduced. and the reduced bead angle, that in turn will be helping to reduce the stress concentration. So, that is about the idea of the remelting. If the bead angle is again too high, then what we can do? We can do the machining of these areas wherever the bead angle or the fillet radius is very less. So, we can do the machining in those areas in order to reduce the stress concentration. So, the peening or hammering can help to eliminate the locked in strain as well as to realize the desired surface profile. The remelting can help to eliminate the defects, and machining also can help to eliminate the high stress concentration, especially at the toe of the weld. Okay. So, now if we see, these are the three examples related with the machining or the relocating the joint. Say this is a typical T joint which is being made, and if the fillet joint is made like this, if there is a fillet, so high stress concentration will be there at the toe of the weld. So, if the toe of the weld is machined using this by giving the proper radius to the tool, so this will ensure the gradual transition of the stresses between the components which are being joined. Okay. And so, this is this kind of the machining for reducing the stress concentration will help to reduce the stress localization at the toe of the weld, and thereby it will help to improve the joint performance. And if we can relocate the joint, like initially here for T joint we are having the fillet radius. If the fillet joint can be replaced with the butt joint, then the performance of the joint will be enhanced significantly. So, in this particular case, the T joint has been redesigned, and the two fillet welds has been replaced by the three butt joints. Okay. So, this will the location of the joint will change, and the type of the joint will also change, because the fillet joints come with the fillet welds come with the inherent stress razors at the toe of the weld, which is not the case in case of the butt joint. Okay. So, that is why proper type of the joint or relocation of the joint helps in improving the joint performance. Okay, this is just a schematic demonstration of like how the TIG dressing works in, like say there is a weld joint, okay, between the two components. So, in the weld joint, like say there is a porosity and the inclusions, okay, and that we can see all along the weld near the toe. So, what if the heat source in localized way, means TIG arc is passed through the toe of the weld along this the toe of the weld. So, this will be causing the remelting of the weld metal near the toe. Okay. And when it remelts, your the inclusions, cracks and the porosity, everything is eliminated. Okay. At the same time, due to the remelting, we are able to reduce the fillet radius also. Initially it would have been like this, but thereafter after remelting this will be reduced. So, that the stress concentration at the toe of the weld is minimized, and discontinuities are also eliminated. But for this we need to certainly optimize the heat input, so that only the thin layer of the metal weld metal near the toe of the weld is melted, and unnecessary thermal damage to the weld metal and the base metal is minimized. Okay. Now, here reducing the residual stresses, as I said, in fusion welding what we get, like so this is the fusion weld joint, and maximum certainly the heat and maximum temperature is generated at the weld center, and then it will be decreasing away from the weld center. So, because of this, the differential weld thermal cycle is imposed to the parent metal in the different zones, and as a result of this what we get? We get the residual stress distribution like this. Okay. So, that maximum residual stresses of tensile type developed at the center, and also little bit in the weld zone also is covered with the tensile stresses, but it will be decreasing as we move away from the weld center, and then balancing stresses will be there in the base metal or in the heat affected zone. So, the point here is, if the residual stress of the tensile type, tensile residual stresses are already therein, then this will reduce the load carrying capacity of the weld joint. Okay. And greater the residual stresses, lesser will be the load carrying capacity. Okay. Because these residual stresses work in algebraic way, like if the load carrying capacity of the joint is say 50 units, and the residual stresses is of 20 units, then the actual load that we can apply will be just 30 units. If the residual stress is minimized to 10, then our load external load that can be applied can go up to the 40 units. If the residual stress is 0, then we can go up to the 50 units. Otherwise, what will happen? The things will deform and the joint will fail. Okay. So, it is important that the residual stresses are minimized, especially the tensile residual stresses are minimized. Because if this is not done, then what will happen? This will be promoting the distortion, like the change in shape of the plates which are being joined. That is one. It will certainly, as I have described, it will be reducing the load carrying capacity of the weld joint. Further, if the metal is hard and brittle, then it will increase the tendency of cracking. And if the joint is to be used in the corrosive environment, then in presence of the tensile residual stresses, it will be promoting the stress corrosion cracking, okay, commonly known as SCC. So, all these undesirable effects can be there in the weld joint if there are residual stresses in the weld joint. So, this is what indicates that residual stresses must be minimized, because residual stresses reduce the mechanical performance, promote the stress corrosion cracking, and if the HZ is hard and brittle, then it will promote cracking and it will increase the distortion tendency. Okay. So, what we can do for reducing the residual stresses? There are multiple methods. One of the most commonly used method is the stress relieving treatment. Okay. So, stress relieving treatment is one where the thermal treatment is given. Okay. Thermal treatment is given depending upon the metal system. Okay. As per the metal, we heat, okay, heat up to the less than the critical temperature, as per the metal. We do not want any kind of the phase transformation or much alteration in the properties. Okay. Say in case of the ferrous metals, maximum heating for the stress relieving can be done below the lower critical temperature. But in case of the aluminum, also we have to see that unnecessary dissolution and reversion does not take place because of the stress relieving. So, depending upon the metal system, heating is done. So, what happens when we heat the metal? Okay, increasing the heating will increase the temperature, and that in turn will reduce the yield strength. Once the yield strength is reduced, then locked in strain, which was contributing towards the residual stress development, that will be reduced. And once the locked in strain is reduced, then our residual stresses are also accordingly reduced, because E is the material property and E is the locked in strain. If this is getting reduced, then the related residual stress magnitude will also be reduced. So, this is simple logic. Higher the temperature, greater will be the reduction in the yield stress, greater will be the relieving of the locked in strain. So, greater will be the reduction in the yield stress that will be, greater will be the reduction in the residual stresses that will be realized. And similarly, the localized yielding is attained through the overloading of the weld joint. Overloading means the joint is loaded beyond the yield point, so that the localized yielding take place in order to relieve the locked in strain. And similarly, ultrasonic treatment is given so that the resonant frequency is attained and the locked in strain is relieved to reduce the residual stresses. So, we can see here, if we have, like say, the stress relieving, increasing the stress relieving temperature. So, initially even the temperature is less, the maximum residual stress first can be maximum up to the residual stress magnitude can be maximum up to the yield strength. So, if we do heating little less low temperature, then the reduction in the yield stress is marginal. But if we increase the heating temperature, then there will be significant reduction in the residual stresses or significant relief in the residual stresses that will be obtained. And further higher temperature if used for the heating, say in case of the ferrous metals, this is applicable for the ferrous metals weld joint. So, the residual stress will be reduced like say 90 to 80 to 90% on heating to the higher temperature. Further, if we heat it for longer time, then there will be greater reduction in the yield strength for any given temperature. So, for 2 hours there is a little say 50% drop at this temperature, and then if we heat it for the 4 hours, then further lesser residual stresses will be obtained, and the further more stress relieving be there if we heat it for a longer time. So, here there are two things, one is the temperature and another is the time. Longer is the time, greater will be the stress relieving, higher is the temperature, greater will be the stress relieving. But we have to see that because of the stress relieving there is no major microstructural change, otherwise that will affect the mechanical performance of the joint. Our target is primarily to relieve the residual stresses. Now, here I will summarize this presentation. In this presentation, basically I have talked about the various approaches to be used for improving the joint performance and what are the methods can be used for reducing the defects in the weld joint and what can be done for relieving the stresses. Thank you for your attention.